the next logical development on Sangria. So folding lookups and high degree custom gates. So yeah, if you want to take it away.
Cool. I guess I'll start. So yeah, so hi everyone. A couple of just things to set the tone first. At least talking for myself, I'm a mathematician first. So like when I do things like this, I'm probably not as aware of other surrounding, like, oh, what's hot this week in ZK or whatever, as I should. But you know, hopefully we can all learn together by talking about things like that. But I'll be mostly focused on the technicalities of the particular problem we've solved. And the other little disclaimer is this is very similar to a talk we recently gave at Zuzalu ZK Week. So if you were there, then sorry, it would just be a mildly updated version of that. Okay, with those disclaimers aside, let's start. So for me, kind of the way I like to think about this folding stuff is like they all come from a wishful thinking kind of direction. And I know you guys might have seen Nova and Sangria already. So hopefully this is a slightly different perspective. I'm not sure. So basically the thing I want is, suppose I have this Nova, the R1CS relation, this AZ1 circ BZ1 equals CZ1, and also AZ2 circ BZ2 equals CZ2. What I would really like to be able to do is if the data were folded up with this linear combination with respect to R, that the original algebraic relation would just still work. But this doesn't work. And this is why in Nova, we relax and introduce two things. We needed 2 degrees of freedom. One is this coefficient in front of the right-hand side, and one is an additive thing to the right-hand side. And luckily, having these two is enough. So this is how I think about having this relaxation. You replace any right-hand side by u times it plus e, and as in this picture. Okay, next slide. So to get, right, so like, and now it's actually just how to solve for it, which is just a algebraic problem. So we just multiply things out, and then you realize, oh, there's this r squared term that's roughly what we want. And then there's this r term in the middle. And that means if we like solve for what the error term is, the coefficient, the u's appear nicely as this u1 plus ru2. That's kind of what we wanted. And the error term is this e1 plus r1 e2, r squared e2 plus b, where b is this linear term that just happens when it's like how far the thing is from a linear function. So if you just follow the algebra, it looks like something like this. And you know, we can always come back here during the Q&A if people wanted to work through it in detail, but hopefully I sketched the main ideas here. Okay, so how does Sangria work? Again, it's really cool that you've seen it already, but to phrase it in the same way, the thing that we want but can't have is, you know, in the form of these QIs, you have this sum of the QL, QR, QO, QM, QC, both multiplied by a linear, possibly quadratic polynomial in A, B, and C. And what we really want is if you just substituted their linear combined version, the AI plus RAI and so forth, it would just naturally work. That should be RAI prime, sorry. But this doesn't work, and instead we just add a UI in front of everything, and then have an error term on the right instead of 0, and then that kind of does work. So that's the setup, and hopefully at least a partial review. I'll give it to Aardvark now to talk about how do we actually do the custom gates.
Right. Maybe before I start, do people have any questions so far? Okay. So we've done this folding thing with Nova. We've done it with Sangria. I guess we did that's folding with Planck. And Sangria also suggested you could kind of fold almost any sort of gate. Whenever you have a gate that's let's say some polynomial condition, f of z equals 0, well, the dream is you hope you could maybe take in a linear combination of 2 z's And you'd like to have f of z1 plus rz2 equals 0. But of course, algebra doesn't work that way. So what you do is you do this bit of algebra. We can come back to this in the questions, but we do this bit of algebra that lets you handle f of some linear combination at the cost of you have to add in this homogenizing this scale factor u, and you have to throw in a handful of error terms of cross terms bk, where the number of cross terms is one less than the degree of your polynomial. So we've been looking at quadratic polynomials f, so you have one cross term, but as the degree of the polynomial goes up, you have to deal with more and more cross terms. So let me just do a simple example. So let's say you have a custom gate that verifies this cubic equation, that verifies x cubed plus y cubed equals z. And now let's say you have two solutions to this equation. So you have two witnesses for your gate. And you want to take some linear combination and say that your linear combination is again a solution to the equation. So first you make the relaxed gate. So to do this, you make the equation homogeneous. This you have degree 3, you have x cubed, you have y cubed. So you need to throw in a u squared, right? U squared z. You get x cubed plus y cubed plus u squared z equals an error term e. And then you work out the algebra. I didn't show it here, but you work out the algebra. You have these two cross terms, b1 and b2. And then what'll happen? Well, the prover, you commit to your x, your y, your z, your b1, your b2. And then when you get the folding challenge, you fold as follows. X, Y, Z, U become linear combinations. And then the error term gains an r times b1 plus r squared b2. So this is just an example of this general piece of algebra that we saw already with Nova and Sangria. Any questions so far?
Sorry, where's the r cubed coming from in the coefficient of E2?
Where's the r cubed coming from? Because you compute, it's not written here, but you compute x cubed plus y cubed minus u squared z. And because you have x cubed and y cubed, when you expand x cubed, you'll get an r cubed, x2 cubed, and so forth.
Yeah.
Okay, so let's move on to maybe a more substantial example. So these are lookups from Halo 2. So the idea of a lookup is you have, typically you imagine you have a fixed table of things S, and then you have a variable table of things A, a vector, a list of numbers, and you want to prove the assertion that every item in A is actually an S, that you can look it up somewhere in S. So if you look at this first example, S is maybe this list of factorials, and you want to check that every number in this vector A is a factorial, 24, 24, 2, 6, and so forth. And well, there are different ways to do this, but in Halo 2, what they do is they rearrange A and S. They permute them in such a way that, so A prime is a permutation of A, and S prime is a permutation of S. We've just rearranged the entries. But you make it so every element of A prime, every entry in A prime is either the same as the entry next to it in S prime, or it's the same as the previous entry in A prime. So going down the row, this 2 is the same as 2, 6 is the same as 6. Then you repeat, so you have another 6, that's the same as the previous 6. Then you get a 24, which is the same as 24 in S prime, and then you repeat it twice. So you can see once sorry?
Yeah, so let me add a thing real quick. And for this one, you need so the top A prime needs to be equal to the top S prime. It's kind of this inductive statement that either you are you see yourself on the right, or you've delayed the work to the previous guy. But the first guy has no previous guy, so he's like, I must be on the right. I mentioned this just because it will come up in the equations later. So.
Aha, thanks. Okay. So fine. So what do you have to do to check a halo lookup? Well, you have to check that A prime is a permutation of A, that S prime is a permutation of S, and then you have to check this condition that every element of A prime is either the same as the element of S prime or the same as the previous element of A prime. And once you know this, you can see this. This is enough to prove the lookup condition because everything in A has to be something in S. Any questions? Okay, so again, I'm skipping some steps here, but you can convert this into a system of equations. So Z and W, when you check this permutation, right? I said A prime, the column A prime has to be a permutation of A, and this permutation check is done with a random challenge, or maybe with Fiat Shamir. So in other words, the prover sends commitments to A prime, S prime. The verifier sends back, or you take a hash function and you get back some random challenges, beta and gamma. And then using that, there's a grand product argument. I won't get into it, but the prover constructs these additional vectors Z and W. And so what happens, eventually this gets translated to the system of equations. You have 4 equations here. The first 4 verify the permutation condition. The first 4 and the last 2 verify the permutation condition on A and S prime. And the 5th and 6th equations here verify that A prime, that each element of A prime is either the same element of S prime or the previous A prime. So fine, so the upshot is we've converted this to a system of polynomial equations. Don't worry about the Q's, they're basically just row selectors. You can imagine they're all 1. We've converted to a system of polynomials of degree at most 2. You have some of these equations are linear, some of them are quadratic. And as long as these polynomials are satisfied, your permutation condition is satisfied. So we relax them. We have quadratic equations, and so we introduce a U to homogenize. We introduce error terms. The first 5 equations were quadratic. The last 3 were linear. If you're linear, of course, you don't have to add an error term because linear equations play well with linear combinations. But fine, you get these relaxed equations. And now with these relaxed equations, you can run folding just like in Nova and Sangria. There any question? I'm going to pause once more for questions.
Yeah, can you jump up to the previous slide? I'm just curious about the last 2. Yeah, okay, so the last 2 equations, if you by swapping out 1 with U, that shouldn't still evaluate to 0, I think. Should it?
So sorry. So when you go from the equation to the relaxed equation, right? You start with a solution to the equation and you make a solution to the relaxed equation by plugging in U equals 1.
Okay, yeah.
Yeah, you plug in 1 for U and 0 for the error term.
Right, but the general case is in the next slide.
So the general case, that comes when you
And there,
fold.
shouldn't those have error terms there? Sorry, like on the other side of the last 2 equations rather than 0.
No, because they're linear. So if you take 2 solutions, you have Z1, U1 and Z2, U2, and you take a linear and say they both satisfy this, that basically means Z1 equals U1 and Z2 equals U2. Then when you take a linear combination, it'll still be satisfied.
Okay.
So, right, so for linear equations, these last 3 equations are linear, you don't need any error term. Right, but you do need the U. The reason you need the U, I mean, I said a second ago, whenever you have a solution to the the plain vanilla Halo equations and you upgrade them to relaxed equations, you plug in u equals 1, but when you take this linear combination, of course, u will become something other than 1. So that's why you need the u. Okay, I want to give an example of what this looks like for two actual lookups. So here are two examples. Here's on the left, we have the lookup we had before. And then in the middle, I made up a second lookup where you have a different vector of things that are also all factorials. And fine, and let's say the prover commits to these and gets out as a random challenge, r equals 1000. So you just take 1000 times a2 plus a1, and that gives you a, and so forth. And the point I wanted to make here, what I want you to notice is this table on the right, this isn't a valid lookup table anymore. These a's can't be found among the s's. The a primes can't be found among the s primes. A prime is not a permutation of a. S prime is not a permutation of s. The only relation you have among these is the algebra. You have the system of equations we looked at before will be satisfied. So it's not like you're preserving the lookup condition. You're really translating everything into the system of, in this case, quadratic polynomials, and then just doing pure algebra. There are no more questions. Yan, I'll pass it back to you.
Cool. Yeah. So yeah, I wanted to talk about how this actually generalizes and what the contributions here on top of Sangria actually is. Again, just speaking for myself, I feel it's actually fairly minimal. I think we have a kind of a very small iteration from where Sangria is going. So recall that the Halo 2 lookups make this grand product from random challenges, beta and gamma. So let's think about the game turn order. It's like the prover do some computation, and then we get beta and gamma from the verifier, and then we compute these z and w's. And I don't know how familiar you guys are with the product argument, and we can go to details later if you like. But the main idea is z and w's are these products of fractions, and they better equal 1 at the end. So the fact that they equal 1 is like the last couple of equations from the previous few slides, but you should just think of these products of fractions and whatever. But yeah, so this is actually the thing that makes our situation not a direct special case of the custom gates. And again, to give credit for where it's due, Sangria already outlined the custom gate strategy in their paper. So, you know, they did have that idea. So, but it's like the custom gates don't have this weird thing where some of the information is given later, and you want to worry about like not giving away too much information first so that the prover or the verifier can cheat. You know, like in cryptography, you have to be a little bit careful about this kind of stuff. So yeah, so to avoid the prover cheating before getting the beta and gamma, you really need for the prover to commit the work they have done so far before getting beta and gamma. It's not like we have a specific attack in mind, but it's kosher to do to commit the information right before you do the next step of calculation with it. And the other thing like we kind of want here is we would like to be able to fold the beta and gamma as well, because you know that's going to be some linear growth of things to keep track of if we are folding like a million calculations together. So this is why we have to kind of upgrade the Sangria sketch a slight bit to do this thing that we call like custom gates with verifier randomness. So yeah. Yeah, so here's kind of the workflow. And in the HackMDs we have, and kind of the more academic-ish PDF paper that's in progress, we'll write this out in kind of more detail. But the workflow here is we're going to have two kind of stages per round, separated by these injections of randomness. So instead of just like folding things one at a time, each turn we kind of do two things. The prover needs to make and then commit the A prime, S, and S prime, because that's all the work the prover is able to do without the additional information. And then you can think of the vertical lines as where the prover got the information she needs to compute the rest of the thing, which is beta and gamma. And then the prover computes and then commits Z, W, the error terms, and the cross terms. And then the beta and gamma is that, then you can think about trace as kind of eating this up, and that is also carried along and folded just as other variables. So the main thing here to just care about is like information hygiene. You know, it's like we want to be we want to be careful about people should not have too much information at any given time. Okay, next. Yeah. So right, so as our final slide, so what happens is in general, we should think about the the lookups as a special case of this folding with in-circuit randomness. The prover first computes and commits this thing called a partial trace, which is like kind of all the work the prover can do. In our case, is the AS, A prime, S prime. Then the prover receives the verifier randomness or other input. It doesn't even have to be random. It's just the only situations we can think of is when they're random. In this case, R, which we call beta and gamma before. And then the prover is able to compute Z and W. And then like that gives a full trace T, and then that could be folded as in Sangria or Nova, and etc. Notice that this could also be theoretically generalized to having many layers of in-circuit randomness. For example, you can assume there's K rounds inside one round of folding where the prover computes something, gets something from the verifier, computes something else, gets something from the verifier again in like a very long multi-step process. And then the little flowchart we had kind of in the last slide, instead of having 2 boxes per step, it'll have like K boxes per step. We just haven't really found a important use case for that yet. And then just kind of a slight shout out and looking forward, we had a lot of good conversations here with Lev Solikov and also Nico from Geometry who did Sangria. And I think they have like generalization ideas that actually overlap with what we're doing here. So at least collectively as a group, I hope you can expect something from some union of us coming up with like a more generalized version of this that can do more interesting things. So Lev particular, he has a protocol in mind that I think goes in a very similar direction as this 2-step thing that we have here. Cool. So if I can share the screen, I can give you a slight demo of what the folding stuff looks like. So let's do that. All right. Hopefully you guys will be able to see this notebook I have open. So yeah, I'll just rerun this to show that it's kind of fresh. So let's see, what did this do? I have kind of a lookup example here where we're looking up odd single-digit integers. So A1 33317 should be successfully looked up in 13579. And A2 is a different instance, 55337, also trying to be looked up in 13579. So in our protocol, which we call origami, we're going to create 2 folding instances out of them. So the folding instances are the things I talked about. We talked about before, where we relax the instance and get more information. So to just look at what they even came up with, this required this like beta and gamma, right? And it is also now a U and a E's. And furthermore, part of the process is constructing this the A prime and S prime, the permuted versions. So as you can see, my little algorithm here kind of permuted 33317 to 13337 and S into 13957. And if you can just mentally imagine putting these 2 columns next to each other, they will have the property that Aardvark was talking about before. The first one equals this one, and then for every element here, is either equal to the element right to the left of it, I guess, or the corresponding element in the S prime. And then this creates these Z's and W's. The main thing to notice is they always end with 1. That's how you know the permutation check has worked. And that also corresponds to some of our equations. And then these 5 error terms. notice these error terms are 0 because we got these instances from actual folding instances. If we fold things up, that's when the errors start to accumulate. So this is not a bug yet. And one thing we'll do is fold them 3 times. And this has to do with the fact that if you're familiar with the soundness proofs of these cryptographic protocols, we are always going to have this concept called an extractor, which you want to extract multiple timelines and to see if you can recover the original information. I'll explain that in a little bit more detail, but the only thing you need to know right now is like, I'm going to do it 3 times and there'll be a reason. So we fold 3 times, and notice that 3 times we're using kind of, there's going to be different R's used to combine them, 178, 234, and 240. And each time you get a new folded instance. It has some U, no longer 1, some beta and gamma of its own is now folded. These A, S, A primes, and S primes that as Aardvark showed earlier in the table, they don't look like lookups anymore, but somehow the math is embedded within this, which is pretty cool. And notice that the errors have begun to accumulate, okay? And the sharp-eyed viewer will see that the E3, E4 are zeros. And that's kind of an artifact of the fact that we're not doing zero knowledge. Since we're not doing zero knowledge, the algebra just works out that these E's are zeros. So you can think of that as an optimization if you want. But if we do insert zero knowledge, I think the way the math works out is going to probably have random errors in there later. That's why we're leaving it in. But anyway, there's 3 folded instances of these 2. So now I'm going to show the extractor, which is a cool part. The extractor is a thing that that shows you that in this sense, you actually have the information. Meaning, if some alien comes to Earth and then just gets my 3 folded instances, the alien should be able to extract the original information. Because as you do this, like the main complaint I always had is, it seems like we're putting everything in this one matrix. We must be losing information somehow, right? Well, it looks like if the alien did have these 3 instances, they can do a kind of linear extrapolation and back out the original extracted instances with just the folded instances. And indeed, you realize that when they extract an instance, they do have this U equals 1. And then they have this, they get one where like the E's are indeed 0. And then they have the original A's and S's, the 33317, 13579, 55337, and 13579 as well. So somehow this actually works, which is great. Okay, cool. I think that ends our little demo, but also the presentation. So I'm hoping we can just do kind of a Q&A with the next part. Any questions for us?
Guys, first of all, I want to say that I think it's pretty cool that you implemented the knowledge extractor.
Yeah, thanks. Yeah, it was fun.
So can you all hear me?
Yeah.
Yep.
Okay, so my question is, have you given some thought to how you might do selective verification here, as in, given a specific one of the instances that contributed to the folding, construct a proof which takes the proof for the folded instance and adds some additional information that allows the verifier to check just one of the instances that contributed to the folding?
I've not thought about it. Yeah, that was. I think you can probably do it with some combination of like taking good partial states, like a partial summation, just break it down into a local computation. But yeah, I'd be pretty interested in talking about this kind of thing after. Yeah, the people we talked to so far did not seem to have a demand for that, but I think this sounds like an interesting use case. Did you have thoughts, Aardvark?
No, yeah, I guess I never thought of that as something you would want to do. The way I see it, I thought this was the whole benefit was that you can check them all at once. So I haven't thought about that.
I mean, I guess an example of a use case of this could be like, you have a bunch of different clients, like say, or they all want something proven about the ledger, but they don't care about each other's facts. They just care about their own.
Your connection is not the best, Morgan.
I
Sorry.
do think that makes sense though.
I'm curious about how are you going to implement so you basically have sort of interactive gates because you need to, well, in practice, fiat shamir it. Is that going to look like something like a hashing subcircuit / custom gate kind of glued to the end of the lookup gate, or how are you thinking about that?
So there's, in this sort of paradigm, there's folding and there's IVC. And folding just means you take two, you have two instances you have kind of two witnesses you want to check, and you fold them into one. But there's sort of this external work you have to do involving a verifier and this fiat shamir challenge where you kind of check that the folding was done correctly. And that's kind of the paradigm we're working in. So we say, you can fold these two things, but you have to do some additional work to check that the folding was done correctly. Now, like the Nova paper also has this idea of IVC where you can actually sort of do all of that in circuit. In other words, in circuit, you do the folding and you check, you kind of check that your fiat shamir hash was constructed honestly, and you check that the folding was done correctly, and you do this over and over again. And you could do that too, but you could do that too, and then you would have to kind of do it all in circuit. Did that answer your question?
Maybe I'm misunderstanding, but I was just thinking about the particular slide where you showed the way that the gate itself is essentially interactive, consists in 2 steps.
Sorry, the particular slide where you showed that the gate itself.
Yeah, it's the
Probably
second,
the
yeah,
12.
that one.
Yeah.
This one here?
Yeah,
Okay.
that one. Okay, I think. Yeah. I'm just thinking from the wrong paradigm, I think, where you just compress everything into polynomials rather than doing the computation step by step. Yeah, this works within the folding theme paradigm, the way you explained it.
Yeah, but I think you do bring up a good point, because if we're going to do IVC, as Aardvark said, then you really do need an in-circuit fiat shamir. And I think one of the conversations we've been having over the past few weeks is like that could be pretty costly. I mean, depending on implementation. So it's just like, do you really save much by doing the folding at the cost of another fiat shamir, or do you not? And I think like that's a natural next step. And probably my personal weakness is just like thinking about the runtimes of all this, because I'm not as native to the engineering part. So just I don't have a very good sense of how costly things are. I tend to think in like big O's, but I think here we have to get a little more brass tacks than big O's. So, but that's definitely something that I think we'll be working on next.
Yeah, I was going to ask about that in general as well, what you estimated in terms of runtime. You also do have to sort these arrays, which I mean, you can do in quasi-linear time.
Yeah, I mean, I feel the array sorting is pretty small compared to like, well, there's like the final verifier stuff, and then there's dividing by a polynomial at the end stuff. There's like some FFT there, like, yeah, those things are probably going to be dominant terms. Yeah, and yeah, I'm guessing those would be bigger than the sort.
My vague heuristic on this sort of thing is that the slowest steps are often the ones that require kind of work on the cryptographic level with the elliptic curves, or maybe with your KZG polynomials. And the first step where the prover kind of fills out the table of witnesses, that's something that can just be done as a direct calculation without working with elliptic curves at all. And so I think that kind of goes hundreds or thousands of times faster than an analogous thing involving elliptic curves. So I'm not actually worried about that first sort at all, I think.
Yeah, I think that's right.
I had a maybe dumb question. So if you want to do this, I think in the examples you just had sort of combining lookups for individual columns. If you want to do multi-column or vector lookups, I assume it's like just as simple to generalize as it is in like the Halo 2 or lookup arguments. I guess you have to fold like additional random elements, but there's no like further complications.
I thought about that. That sounds right to me, but I haven't thought about it in detail.
Yeah, like but that would definitely be the kind of thing we try to write up clearly next or something. We just want to get some sort of MVP with this folding, but yeah. Yeah, it'd be cool if I feel that would what little I know about that would also fit nicely within this multi-tiered framework that we had outlined in the last couple of slides. So hopefully we have the right generalization where that also ends up being a special case.
Cool. Yeah, thanks.
I have a quick question about you mentioned that there would be a more paper-like version of the whole work. So I'm wondering where I can find that. And moreover, if I want, okay, I can. Okay, I found out. Yeah, I see that. Yeah. Moreover, I see you show some example of the code. Yeah, I'm wondering. Do you have any plan to open source that, or
yeah? So quick thing on the write-up, like we have the 2 HackMDs, which I think actually has a lot of the content. It's just maybe not fully academic or whatever. We're working on something that might hit the archive next couple months, fingers crossed, with some other information in it. As for the code, yeah, I mean, like, I feel because the code doesn't, do any of the elliptic curve stuff or any of the serious stuff. It's mostly, I think, just code we scrap together for kind of a proof of concept. But if it makes sense, yeah, I'd be totally happy to share it. I would probably want to make it more readable, but yeah, we're not gonna try to hide this code or anything. It's just right now I don't think it does much, except say the demo I gave you.
Yeah, because if you have some paper-like thing, I may be able to use your work in my current work. But if not, it's really hard to set something medium. So
yeah. For now, if you need to cite it quickly, you can use the HackMDs. But yes, hopefully the paper will come out.
Yeah, but if I say something from the HackMed, it's, let's say, people will ask, how can you prove that it's correct? So
yeah.
It's quite bothering.
No, but bugging us like this is probably the right way to make us finish it faster. It's just people move pretty quick in ZK, so it's just like, as an academic, my timelines are just slower, and it's like, man, people are so fast here.
That's crazy. Thank you.
Talking about the, efficiency, you have a Python POC. It's not gonna, the benchmarks of that don't really matter. Are you gonna work on it in something that's slightly more comparable, like Rust?
So, right. So there's a couple of things there. And I don't know how much of a secret. I don't really think they are. So as mentioned before, Lev from I think Ethereum PSE has a similar thing, and then I feel they're trying to do theirs in Rust. I personally like find the theory stuff more interesting, but yeah, if the like if I get inspired to write something up, then sure. But I don't currently. Yeah, I feel currently there's just like a few plausibility questions to be answered. Like we can probably do some big O stuff without benchmarking like actual code. So I probably want to do that first. And then we probably want to, there's like new stuff coming out, right? There's like Hypernova, there's like this other stuff, like things are moving pretty fast. So before committing to kind of a long-term programming project, I still want to see after the dust settles a little bit on what makes the most sense to do, just from a strategic perspective. But yeah, definitely, I think any benchmarks on this Python stuff would not be representative.
Okay, if we don't have any more questions, I guess I'd like to thank you both. Thanks very much for joining us. And
Wait,
great
I do
to-
have a slight other thing. So Yan,
just
you're
a
a
bit.
mathematician, you said. I was just curious because I read on the HackMD and I was so confused about the use of the Laplacian, the triangle notation for the operator you use there. Was there, I mean, with multidimensional polynomial or multivariate polynomials of that triangle, I immediately think Laplace operator. Was there a thought behind that?
So well, first of all, we're both mathematicians, so and so I want to just get that clear. And then two, like that delta notation is, I think, pretty common for this context in a thing called difference calculus. So I imagine, and Aardvark wrote up that part, so he really should talk instead of me. But I imagine that's where he got it from.
Yeah, I was thinking of it as being analogous to some sort of difference operator. So, I mean, you have the idea first and you need a symbol for it, and you want the symbol that kind of suggests the best thing. And in this case, was it a delta or a nabla? It was a delta, right? When you have a polynomial f, you can define a polynomial delta f. It's not exactly the derivative, but it kind of looks like a derivative, by saying you take f of x plus 1 minus f of x, just the difference of kind of values, consecutive values of f, so to speak. And so, if f is a polynomial, then delta f will be a polynomial of degree 1 less. And that was kind of what inspired this, because it kind of sort of felt like the same sort of thing. That's all. It's unfortunate.
Okay, I think that's justified.
But it's not.
It's justified. I was just thinking Hodge cohomology, and I didn't get it. So good to get that clarified.
No, we're not in that universe here. No.
Okay.
Just to math nerd snipe myself a little bit, there is a way this is an actual derivative. Like, you should think about this operator as fx plus 1 minus f of x, with the denominator being x plus 1 minus x. Because if you think about how to define the derivative as a limit, you have this x plus dx, right?
Mm-hmm.
So here the dx is 1 because it's discrete, so the only moves you can make is 1. So the bottom just happens to be 1 because it's x plus 1 minus x. So there's like some actual semi-algebraic sense in which this is a derivative, and therefore you can kind of do calculus C things with it. But anyway.
That was pretty nice. Appreciate it, guys.
Thank you.